Alrighty folks, in this lecture I'm going to start relating phasors to resistors, inductors, and capacitors. And then in the next lecture we'll start applying that to real circuits. So the first question we should ask is, how do we apply phasors to the circuit elements we know? Tap, tap, tap. All right, I think that's a pretty good question because this is meant to be an AC circuits sort of class, or at least this portion of the class is AC circuits. So what I'm really hoping to do is get you to a point where you are working with actual circuits and not just complex numbers, our phasor representations. So let's start with a resistor. This one is possibly the easiest and the thing that we've seen the most in DC circuits. So let's allow current to be I, which is Im cosine omega t plus phi. And then V, because of Ohm's law, is equal to that current times the resistance, which is the same as R times Im cosine omega t plus phi. So in phasor form, the phasor version of V is just R times Im angle phi, but Im angle phi is the same thing as I phasor. So that implies in phasor form, V phasor is equal to I phasor times R. That looks exactly like the Ohm's law we have come to know and expect. If I'm to construct a phasor diagram for a resistor, what that means is, if my imaginary axis is the y-axis and my real axis is the x-axis, what that means is that I've got maybe a voltage V phasor, and then on top of that, with the exact same phase and angle phi, I have a current I, and they are related by some proportional constant. So this is for a resistor. This is the perfect opportunity to make my terrible joke. Why did Cap make a capacitor? Because he couldn't resistor. So speaking of capacitors, let's talk about capacitors. In a capacitor, let's assume the following. Let's say I have a voltage. It's equal to Vm cosine of omega t plus phi. I know that the current in a capacitor is the capacitance C times dV dt. So let's go ahead and take that derivative. That's equal to the capacitance times negative omega times Vm sine of omega t plus phi. To convert that into cosine form, this is equal to negative omega c Vm sine of let's convert it to cosine, my bad. So negative omega c Vm cosine of omega t, and I get there by taking minus 90 degrees. But I want to get rid of this minus sign, so I'm going to add or subtract 90 degrees from this. So this is omega c Vm cosine of omega t plus phi minus 90 degrees, let's say plus 180 degrees. So that's equal to omega c Vm cosine of omega t plus phi plus 90 degrees. Now, let's go ahead and convert this into phasor form. I phasor then is equal to omega c angle phi plus 90 degrees. Now, something that is interesting is that one angle 90 degrees is just equal to J. To demonstrate that, I know that J is equal to 0 plus J times 1, which has magnitude square root of 1 squared plus 0 squared, and an angle inverse tangent of 1 over 0, which is equal to 90 degrees. So, since that's true, I can pull this, and that's multiplied by V phasor up here. I can pull out this 90 degrees, and I've got I phasor is equal to J omega C V phasor. I'm really bad at this today. This isn't V phasor, it's VM, but I know that VM angle phi is equal to V phasor. So, if I want to write this in an Ohm's law-like form, that means that V phasor is equal to 1 over J omega C I phasor. That's my Ohm's law-like form. And if I draw a Phasor diagram for this, I'll have my voltage, which I think that I used orange for before. I've got my voltage, which is right here. And then I've got my current separated by 90 degrees from that. That voltage has a phase phi. I phasor is separated by 90 degrees from V, and it turns out that, so right for a capacitor, it turns out that we can say the following. In a capacitor, I leads V by 90 degrees. Now there is a fun mnemonic device to remember this. I'll put it together in a little bit, but I've got two ways. The first is ICE, where I stands for current, C stands for capacitance, and E stands for EMF or voltage. So I leads V by 90 degrees in a capacitor. The other one is CIV, where in a capacitor, that's C, current leads voltage, I leads V. So the final one of these elements that I need to talk about is the inductor. This would be a time for another joke, but I'm not going to make that because this is going out to everyone. So, in this situation, I'm going to let I equal to Im cosine of omega t plus phi. I know V is equal to L di dt, and using the same sort of method as I did before, I will find that V phasor is equal to J omega L I phasor. That's my Ohm's law expression for an inductor. That was a really long pause. Sorry about that. So I can draw my phasor diagram for this in the same way I've done earlier. In this case, again, real axis on the X, imaginary axis on the Y. And I've got my voltage, which is usually the first thing I draw. I'm actually going to do my current first. And I've got an angle phi for my current. And I'm just going to make a note, this is for an inductor. And then I've got a 90-degree separation to V. So make sure I clear that up. I've got a 90-degree separation, and so what we can say is that in an inductor, V leads I by 90 degrees. V leads I by 90 degrees. Again, mnemonic devices. So ELI, that's my happy little mnemonic device for the first thing here. E is EMF or voltage, L is my inductor, I is current. And similarly, I've got VIL, voltage leads current in an inductor. So I can put those mnemonic devices together. So I've got two options. The first one is ELI, the Iceman. If I can remember ELI, the Iceman, I know how voltage and current are related in an inductor and how current and voltage are related in a capacitor. The second mnemonic device is to remember civil, CIVIL. So in a capacitor, I know that I leads V by 90 degrees, and in an inductor, I know that V leads I by 90 degrees. And that, by the way, is the most useful that civil will be in this class. All right, so let's summarize this into a nice little table for you to remember. So let's summarize this. I know that R in the time domain, I've got V is equal to I times R, and in the phasor domain, V phasor is equal to I phasor times R. I also know that for an inductor, V is equal to L di dt in the time domain, but V phasor is equal to J omega L I phasor in the phasor domain. And for a capacitor, I know that V, really the best way to do this might be to say I is equal to C dV dt, and so V phasor is equal to I phasor over J omega C. Let's apply this to one or two examples, and then next time we'll get a little bit more information out of this. So example number 1. Here we go. In this example, I've got a voltage as a function of time. It's 12 cosine of 60t plus 45. 60 plus 45, not 55. 60 plus 45 degrees. Applied to a 0.1 Henry inductor. I want you to find the steady state current. We know actually that in DC, if I apply a DC voltage to an inductor, if the voltage across an inductor is equal to 0, so it looks like a short, as long as there's no change in current. That's the case with DC, but now we're working with AC, and so I should be able to find this steady state current value. So first thing I want to say is, all right, I know V is equal to J omega L times I. The good news is that I've given you omega, it's equal to 60 radians per second. It's equal to 60 radians per second. And so V is equal to, I already have V. V is equal to 12 angle 45 degrees, thanks to the phasor transform of V of t. And I know the value of inductance. I know that L is equal to 0.1. So I know that I can be solved for by taking V over J omega L, which is equal to 12 angle 45 degrees over J times 60 times 0.1. That's equal to 12 angle 45 degrees over 6 angle, and then I've already established in this lecture that J is 90 degrees, so angle 90 degrees. So that means that this current is equal to 2 angle minus 45 degrees amps, and I want to convert this to the time domain. To convert this to the time domain, I say I of t is equal to the magnitude 2 cosine of omega t, I said that's 60t before, minus 45 degrees amps. And I'm done. We can do a very similar example. That's example 2. In this case, I've got a voltage which is 10 cosine of 100t plus 30 degrees, and it is applied to a 50 microfarad capacitor. And I want to find the current in the capacitor. Find I. And specifically, I want to find I of t in the capacitor. Alright, so I know in a capacitor, I is equal to J omega C times V phasor. Omega is equal to 100 radians per second based on my expression up there. So V is equal to 10 angle 30 degrees from my phasor transform. And so I is just equal to J times 100 times 50 times 10 to the minus 6. Gosh, I'm boring. Times 10 angle 30 degrees. I know that J is an angle of 90 degrees, so altogether I know I'm going to get an angle of 120 degrees. And then when I multiply 100 times 50 times 10 to the minus 6 times 10, I'll end up with 50 times 10 to the minus 3, or 50 milliamps. And then the last step is to convert to time domain. And so I of t is equal to 50 cosine of 100t plus 120 degrees milliamps. And I'm done with that example. Alright, in the next video I'm going to talk about impedance and admittance and start applying some stuff to circuits. We'll catch that next time. Again, if you have any questions, feel free to contact me, leave a comment, jump in the Discord server, which is in the description below. I'd love to chat with you on stuff and give you some help. Alright, thanks for watching.